America's interior is not supposed to behave like this. Far from the grinding edges of tectonic plates where mountains rise and oceans open, the central United States appears on the surface geologically quiet. Yet beneath that calm landscape, a buried system of faults is shifting again, incrementally, persistently, and now with a pace that is drawing renewed attention. The question is no longer whether the ground is moving, but how much strain is being stored, how widely it is distributed, and what pattern the recent surge in seismicity may represent. Why is a region known for subtle tremors now exceeding its typical yearly earthquake counts within just a few months? What does it mean when a fault system far from any plate boundary begins to register hundreds of small fractures in such a compressed time frame? And how does a landscape shaped by ancient geological forces continue to transmit stress across distances that defy intuitive expectations? The New Madrid seismic zone stretches across the central Mississippi Valley, cutting through portions of Missouri, Arkansas, Tennessee, Kentucky, and Illinois. It spans roughly 150 miles, or about 240 kilometers, forming a diffuse network rather than a single clean fracture. This distinction is essential. Unlike the sharply defined faults of California, the New Madrid system is a complex lattice of buried structures, many of them concealed beneath layers of sediment deposited over tens of thousands of years. These faults do not express themselves through dramatic surface ruptures in normal conditions. Instead, they release energy through frequent, low-magnitude earthquakes, microseismic events that rarely attract attention individually but collectively map the slow redistribution of stress deep underground. Under typical conditions, the region records on the order of 150 to 250 earthquakes annually. Most of these events fall below magnitude 2, occurring at depths ranging from a few miles to several miles beneath the surface, approximately 5 to 15 kilometers. These tremors are often too weak to be felt, detectable only through sensitive instruments distributed across the region. However, the pattern for March of 2026 diverges sharply from that baseline. The cumulative count has already surpassed 300 events, exceeding the upper bound of the average annual rate within a fraction of the year. This acceleration is not characterized by a single dominant earthquake, but by a clustering of small distributed ruptures, an indication that stress is being released in multiple segments rather than along a single fault plane. Short-term fluctuations are not unprecedented in this system. Data from early 2026 shows variability even within consecutive months. January registered roughly 17 recorded events, significantly below the expected monthly average of around 30, suggesting a temporary lull. February then exhibited an even more pronounced drop, with only 6 confirmed earthquakes throughout the entire month. Such decreases are not necessarily signs of reduced tectonic activity. In many fault systems, periods of relative quiet can coincide with stress accumulation. What follows, as observed in early March, can be a rebound phase marked by clusters or swarms of smaller earthquakes. A documented sequence of multiple quakes occurring within days in March reflects precisely this pattern of release following suppression. To understand why this region behaves in such a manner, it is necessary to examine its geological foundation. The New Madrid seismic zone is not located at a plate boundary. Instead, it lies within the interior of the North American plate, making it an example of intraplate seismicity. This alone sets it apart from most of the world's major earthquake zones. The key to its activity lies in a buried structure known as the Reelfoot Rift, a failed continental rift that formed hundreds of millions of years ago during the late Precambrian to early Cambrian periods. A rift, in geological terms, represents an area where the Earth's crust attempted to split apart. In the case of the Reelfoot Rift, that process never fully succeeded. Instead of forming a new plate boundary, it left behind a weakened zone within the crust, a structural scar extending deep into the lithosphere. Over time, this rift became buried beneath sediments carried by the Mississippi River and its tributaries, effectively masking its presence at the surface. However, the mechanical weakness remains. When stress is applied to the North American plate through forces generated by distant plate interactions, such as the continued westward movement of the continent, this ancient rift becomes a focal point for strain accumulation. The stress regime in the region is subtle but persistent. Measurements indicate that deformation rates along the New Madrid system are extremely slow, on the order of fractions of a millimeter per year, approximately 0.008 inches annually. This is significantly lower than rates observed along active plate boundaries, yet it is sufficient to generate seismic activity over long timescales. The key difference lies in how stress is distributed. In plate boundary settings, stress is concentrated along relatively narrow fault lines. In intraplate settings like New Madrid, stress is more diffuse, often activating multiple faults simultaneously or sequentially. Another contributing factor is the composition and thermal state of the lithosphere beneath the region. Some studies suggest that localized heating or the presence of a dense, sinking body of ancient oceanic crust deep within the mantle may be influencing stress distribution. These conditions can make the lower crust more ductile, capable of slow deformation, while concentrating brittle failure in the upper crust where earthquakes occur. The result is a system in which energy is transferred upward and released in intermittent bursts rather than continuously. The sedimentary environment above the fault system also plays a significant role in how seismic energy propagates. The Mississippi embayment, which overlays much of the New Madrid zone, is filled with unconsolidated sediments, layers of sand, silt and clay deposited over thousands of years. These materials can amplify seismic waves, allowing even moderate earthquakes to be felt over large distances. Historical records from the early 19th century indicate that earthquakes originating in this region were felt across vast portions of the eastern United States, far beyond what would be expected for similar magnitudes in more rigid crustal settings. That historical context remains critical because the New Madrid seismic zone is responsible for one of the most significant earthquake sequences in North American history. Between December of 1811 and February of 1812, a series of large earthquakes, estimated to reach magnitudes of 7 or greater, struck the region. These events altered the landscape dramatically, causing ground subsidence, the formation of new lakes, and widespread liquefaction. The geological record indicates that similar sequences have occurred in the past, with evidence pointing to major events around the years 1450-900 and even earlier. Paleoseismic studies suggest that large earthquakes in this region may recur on timescales of roughly 500 years, although the pattern is not strictly periodic. This irregularity complicates any attempt to interpret current activity as a precursor to a larger event. The presence of hundreds of small earthquakes within a short period could indicate localized stress release, redistribution of strain across fault segments, or the activation of previously quiet structures within the rift system. At present, most of the earthquakes being recorded remain low in magnitude, typically below 2 or 3. These events occur frequently, sometimes every other day, and are considered part of the background seismicity of the region. However, the cumulative increase in frequency changes the statistical profile of that background. Instead of a steady rate of occurrence, the system is displaying clustering behavior, where multiple events occur in rapid succession within a confined geographic area. Clustering is a well-documented phenomenon in seismology, often associated with the redistribution of stress following an initial rupture. When a fault segment slips, it alters the stress field in surrounding areas, potentially bringing adjacent segments closer to failure. In regions with complex fault networks such as New Madrid, this can result in sequences of small earthquakes rather than a single larger event. Each tremor represents a minor adjustment in the crust, but collectively they can signal a broader reconfiguration of stress. The spatial distribution of recent earthquakes within the New Madrid zone suggests activity along multiple segments, including areas near southeastern Missouri, northeastern Arkansas, and western Tennessee. These regions correspond to known fault structures associated with the Real Foot Rift, including the Cottonwood Grove and Ridgely fault systems. The depth of these events, generally within the upper crust, indicates that they are occurring in brittle rock layers where accumulated stress is released through sudden fracture. One of the defining characteristics of intraplate earthquakes is their ability to transmit energy over long distances. The older, colder crust of the central United States is more efficient at conducting seismic waves compared to the fractured heterogeneous crust found near plate boundaries. As a result, even relatively small earthquakes can be felt across multiple states, particularly when they occur at shallow depths. This property has implications not only for how earthquakes are experienced, but also for how stress is distributed within the crust. Because seismic energy travels efficiently, the release of stress in one location can influence conditions over a broader area. This interconnectedness may contribute to the observed clustering of events as adjustments in one segment of the fault system propagate outward. The increase in seismic activity during March of 2026 must therefore be interpreted within this broader geological framework. It reflects not just a rise in the number of recorded earthquakes, but a shift in the dynamics of stress release within the system. Whether this shift represents a temporary fluctuation or part of a longer-term trend remains uncertain, but the underlying mechanisms are rooted in the unique structure and history of the region. The New Madrid seismic zone continues to operate as a reactivated rift, a relic of ancient tectonic processes that remains sensitive to modern stress fields. Its behavior is governed by a combination of factors: the presence of weakened crustal structures, the slow but persistent movement of the North American plate, the mechanical properties of the lithosphere, and the amplifying effects of overlying sediments. Each of these elements contributes to the pattern of seismicity observed today. As the number of recorded earthquakes continues to rise beyond typical annual levels, attention is increasingly focused on how these small events fit into the broader cycle of strain accumulation and release. The system does not follow the same rules as plate boundary faults, where large earthquakes often dominate the seismic record. Instead, it operates through a complex interplay of minor adjustments, long periods of relative quiet, and occasional episodes of intensified activity. The data emerging from early 2026 captures one of those episodes in progress. The transition from below-average activity in January and February to above-average levels in March highlights the variability inherent in the system. It also underscores the importance of continuous monitoring, as short-term changes can reveal underlying processes that are not immediately apparent from long-term averages. Beneath the fields, rivers, and cities of the central United States, the New Madrid seismic zone remains active, its faults adjusting incrementally, its stress fields evolving, and its seismic patterns shifting in ways that reflect both ancient geological inheritance and ongoing tectonic forces. The recent surge in earthquake counts is not an isolated anomaly, but part of a continuum shaped by millions of years of Earth's history, now expressed through the subtle but measurable movements of the present. The current pattern of seismic activity across the New Madrid seismic zone is not occurring in isolation. It is unfolding within a broader temporal framework that reflects how intraplate systems evolve under sustained stress. What distinguishes this phase is not the magnitude of individual earthquakes, but the density and persistence of occurrences within a compressed interval. When a fault system that typically distributes its seismic output across an entire year reaches and exceeds that level within a single month, the implication is not simply increased activity, but a redistribution of strain that is unfolding more rapidly than usual. This acceleration introduces a critical variable: time compression in stress release. In geological systems, the rate at which stress is relieved can influence how adjacent fault segments respond. A slower, evenly distributed release allows for gradual adjustment across the network, whereas clustered activity can create localized imbalances. Each small earthquake alters the stress field in its immediate vicinity, increasing or decreasing the likelihood of subsequent movement along nearby structures. In a system as fragmented as New Madrid, where multiple faults intersect and overlap at varying depths, these interactions can produce cascading sequences that extend beyond the initial cluster. The structural complexity of the region amplifies this effect. Unlike linear fault systems, where stress transfer tends to follow a more predictable path, the New Madrid network behaves as a three-dimensional lattice. Fault planes dip at different angles, intersect at depth, and are embedded within rock layers of varying strength and composition. Some segments are locked, accumulating stress over long periods, while others are more prone to frequent, smaller slips. The recent surge in earthquake counts suggests that multiple segments are currently active, each contributing to a broader pattern of adjustment. Another dimension to consider is the role of pore pressure within the crust. The Mississippi embayment is not only a repository of sediments, but also a region where groundwater is abundant. Fluids within rock formations can influence fault stability by altering the effective normal stress acting on fault planes. When pore pressure increases, it can reduce frictional resistance, making it easier for faults to slip. While there is no singular mechanism driving the current increase in seismicity, fluctuations in subsurface, fluid pressure may contribute to the timing and distribution of smaller earthquakes, particularly in sediment-rich environments. The geological layering above the Reelfoot Rift also affects how seismic energy is both generated and recorded. Thick accumulations of unconsolidated materials can dampen high-frequency signals while amplifying lower-frequency waves, influencing how earthquakes are detected and how their magnitudes are calculated. This means that part of the observed increase may reflect improved sensitivity in monitoring networks, but instrumentation alone does not account for the scale of the deviation seen in March of 2026. The consistency and clustering of events indicate that the system itself is undergoing a measurable shift. Looking deeper, the relationship between the upper crust and the underlying mantle plays a role in long-term stress accumulation. The North American plate is subject to forces generated at its boundaries, including the spreading of the Mid-Atlantic Ridge and the subduction of oceanic plates along its western margin. These forces are transmitted across the plate interior, albeit at reduced intensity. When they encounter zones of weakness, like the Reelfoot Rift, they can become concentrated, effectively reactivating ancient structures that would otherwise remain dormant. This reactivation does not occur uniformly. Instead, it manifests as episodic pulses of activity, separated by periods of relative quiet. The recent pattern suggests that the system has entered one of these pulses where accumulated stress is being released through a series of small adjustments rather than a single, large rupture. Each event relieves only a fraction of the total strain, leaving the broader system still under load. The historical record reinforces the importance of viewing current activity within a long-term context. The major earthquakes of the early 19th century were not isolated incidents, but part of a sequence that unfolded over several months. That sequence included multiple large events, each altering the stress distribution and triggering additional movement along connected faults. While the present activity is far below that scale, the underlying mechanics, stress accumulation, redistribution and release, remain consistent. One of the challenges in interpreting the current surge lies in distinguishing between normal variability and meaningful deviation. Earthquake systems are inherently noisy, with fluctuations occurring across all timescales. However, when activity exceeds established baselines by a significant margin, it warrants closer examination. Surpassing 300 recorded earthquakes within March alone represents a clear departure from the expected annual range, indicating that the system is operating outside its typical parameters. At the same time, the absence of larger magnitude events suggests that the energy being released remains distributed across many small fractures rather than concentrated along a single fault. This distribution can be interpreted in multiple ways. It may indicate that the system is effectively relieving stress in small increments, reducing the likelihood of a larger event in the immediate term. Alternatively, it could reflect a preparatory phase, where smaller adjustments are progressively loading specific segments toward a threshold. Spatial analysis of the recent earthquakes reveals that activity is not confined to a single point, but is spread across the broader seismic zone. This dispersion supports the idea of a network-wide adjustment rather than a localized anomaly. The involvement of multiple fault segments increases the complexity of the system's behavior, as interactions between these segments can produce non-linear outcomes. A small change in one area can have disproportionate effects elsewhere, depending on how stress is transferred through the network. If you found this breakdown informative and want to stay updated on developments like this, make sure to like, share, and subscribe, and tap that hype icon to help this video reach a wider audience.